Good day from Chem Help ASAP. This is my second reaction video. I recently saw a video by Modern Goldsmith in which he refined a bar of just metal into pure gold. So I thought it was interesting. I thought it highlighted some cool chemistry, and so I'm doing a reaction video to that content. I will say I have sped up Modern Goldsmith's video 1.25 times. So I'm playing his audio a little bit faster. I also have some edits in here where I've chopped out some of the ads. So those are two disclaimers. Let's now get into the video.
Banana for scale. This is a huge metal blob. My client inherited it from a family member, and not knowing what it was, the blob was almost thrown away. Thankfully, it was brought to my shop instead.
Wow, so this chunk of metal was almost thrown away. I mean, I have no idea how much gold is in there, or at least at this point in the video we don't, but gold's expensive, and that would be terrible if that got thrown away.
Can I uncover its secrets? Is it real gold? And if it is, how much gold is actually in there? It's really heavy.
Oh, I just missed that. Well, so you can see it. It's about the size of the palm of your hand. It's a pretty big piece of metal.
533.3 grams heavy.
Okay, so 533 grams, that's about half a kilogram, and that works out to be 18.8 avoirdupois, and I think I'm saying that right, avoirdupois ounces. And normally precious metals are metaled in troy ounces, and troy ounce is a little heavier than an avoirdupois ounce. So this would be about 17.3 ounces. So when people say gold is worth $3,000 an ounce, that's a troy ounce, and this is 17.3 ounces. Of course, it's not pure gold, but it's potentially a lot.
Now, the first step in my investigation is to cut a small sliver off of this blob. I'm going to use my gold tester to find out just exactly what it's made of. Using an acid solution, this machine will tell me whether the metal is not gold, 10 karat, 14 karat, 18, etc.
I'm not, this has got to be a jeweler's tool. I'm not familiar with this kind of test, but it's what people use.
Dipping the sliver down into the acid well, I can see that it's very clearly reading 10 karat. But
and that's at least 10 karat. Now maybe it's not 14, but maybe it's 13 karat. So it's looking good. There's plenty of gold in there.
Just to make sure, I want to check my solution with this 18 karat gold ring. Bingo. 10 karat gold.
Okay, so let's jump back just a couple frames here, if I can. So the use of that gold ring, that is something in the sciences, it's called a positive control. So and that does validate his method to a degree. So he knows what that ring is. It's at least 18 karat gold, and so that's his positive control to make sure his method is working. It's always a good idea to have a positive control when you're trying to do some kind of assay.
10 karat gold is 41.7% pure. In other words, 41.7% of this blob is pure gold, which means 58.3% is not. It's other metals, and who knows what else. The mission: extract the pure gold, using chemistry, literal gold refining. But there's just one problem. I'm not a chemist. In fact, I've never even taken a chemistry class.
I love this humility. You don't see a lot of humility on YouTube, but he's very candid. I'm not a chemist, but he knows a thing or two. He's no fool. But when you know your limitations, it makes it easier for you to address those limitations and still have a favorable outcome.
Math tells me that I should be able to extract 222 grams of pure gold.
And I would say at least 222. Optimistically, more than 222, because it's at least 10 karat gold. At least that little sliver was. He didn't sample the entire block, and it's not a homogeneous sample, but it could be even higher.
I think the 222 grams is the best case scenario. I'm actually expecting a lot less than that. In fact, it looks like the blob maybe wasn't even completely melted all the way through. You can see it was kind of fragmented here, the way that it's folded on top of itself. It just kind of looks weird. So I'm really interested to see what the final total is. So let's go ahead and melt this down and start refining.
All right.
Off to a great start.
That is. How often do you do that? You start a task and immediately run into a problem. Even something as silly as something doesn't fit. That's frustrating.
My largest crucible, and the blob won't even fit inside.
Okay, he's not a chemist, but that's a nice torch. It's nicer than anything I have in my laboratory. I'm kind of a propane camping torch kind of person, and this torch means business.
Nothing a little fire can't fix.
He has it speeded up, 4 times speed. Gold melts at over 1,000 degrees Celsius, like 1,060 or something like this. So this is, he's working at this. Looks great.
The blob has imploded down into the crucible, and it's taking an extreme amount of heat to get it into the liquid state. You can see just how much sludge and flux has built up around.
I mean, it looks better already. To see that a lot of that dark impurity color is able to separate. He doesn't have it away yet, but it just with a torch you can clean it up some.
This beautiful golden sun. I attempted to pour some out of the crucible. It didn't go super well, but it's already incredibly satisfying to see just how much junk has separated from the gold. Next, I'll be doing some water casting. Now, some jewelers use this method to create some really cool looking organic shapes. Basically, all you do is liquefy your metal and pour it over water.
Now, I've heard people refer to this as making shot. So you pour the molten metal into water and it finally divides and it makes kind of little pellets or BBs, and making shot. So I'm not familiar with the idea of water casting.
I didn't know it at the time, but I was actually making a mistake here. You see, I don't want this beautiful looking mountain that sort of looks like an erupting volcano. I actually wanted a bunch of small individual pieces. And there definitely are some there, but the majority of the gold all got stuck together, primarily due to the fact that the beaker was too small. There wasn't enough time for the gold to cool properly before it just adhered to itself.
Yeah, that does not look like a gold shot or metal shot.
It really was just a rookie mistake. I mean, it kind of looks cool, I guess. I don't know. Let's turn it and see this. Oh my, the blob has a face. This is the face of the blob. This is the personality of the blob manifesting itself.
So let me get this straight. You took the gold and you put it in the fire and out popped a golden calf. I've heard that somewhere before.
It's alive. And now he's dead. But never dead. Just melted into a new shape.
Easy come,
Gone,
easy go.
never forgotten. Trying the water casting again, this time in a 5-gallon bucket. Yes, these were the flakes I was looking for.
That does look better, but I would just ask, do you have a less beautiful cooler you could use for this purpose? It looks so nice and clean. Throwing hot metal into it. Anyway, it does look better.
This is so much better. And you can see a lot of the darker flux actually separated from the gold as well, which I'm super happy about. I then took all my gold nuggets and boiled them in distilled water. Using a stirring rod, I really wanted to break apart any of the flux and dirt and anything else that was in there that wasn't part of the original alloy itself.
Now, this funnel he's using, this ceramic funnel that his hand is touching, that is called a Buchner funnel. And typically you use that to use it with suction, with a vacuum, to draw the fluid through a piece of filter paper, which is in that flask or that funnel, and then to collect the solids on top. So he's not using that with vacuum. It's not a high crime to chemistry, but it's just a different use than you normally see with that type of funnel.
You can just see how dirty this beaker is. I also used this filter.
So you can see now that he opens this up, there is a piece of paper in there, and that paper is sticking to some of the crud that was in that gold shot that he's made. But and you can see the paper, it just fits nicely within that flat base of that funnel. That's how it's supposed to be used. That's the size filter paper you want. We're going to see it kind of gets different as we go into the video. But again, typically use this with suction.
Filter, which has a filter paper inside, and it did a perfect job at capturing just a lot of that junk. But there's also a lot of gold in there, so I don't want to throw it away. I want to rinse out my filter and my filter paper. I'm going to keep this in a separate beaker, and it's just really fun to see how much the gold is already getting cleaned up. I'm going to deal with this dirtier beaker later. I have a plan on how I'm going to get that gold out of there. Pouring off the cleaner gold into a filter, there's still some bigger black.
Let's scroll back there a little bit. That didn't look like there's no filter paper in there. He's just transferring it from one container to the other. But anything that's fine is potentially going to go through those holes. They're called perforations in that filter plate for the Buchner funnel. So this is, unorthodox, but he's getting the job done.
Still some bigger black pieces I need to hand pick out, but the bigger problem is this dirty beaker that has a lot of really small pieces of gold.
Now, as we get into here, it looks to me like that filter paper is a little bit bigger than the bottom of that funnel. And so you're getting some wrinkles and folds, and those become places where things can slip past the funnel. So normally you want that paper to be just a bit smaller than the bottom, big enough to cover the holes, but not any bigger than the bottom of the funnel.
I was really hoping this black stuff would just be water soluble and just dissolve on its own, but it was being pretty stubborn. So I came up with the idea of just pouring it into this filter paper.
Now, as he pulls up this paper, there is some stuff that has apparently gotten past the filter paper. And that's if the filter paper doesn't fit, not perfectly, but pretty close to perfectly, you are at greater risk of losing stuff around that piece of filter paper.
Folding it up, I'm going to put it in my crucible, melt the whole thing down, and separate the gold from it that way.
Okay, fire fixes everything. Looks good.
And that worked perfectly. I'm super happy that I took the time to get every little tiny piece of gold that was left over, because when you add it all up, it's 17.5 grams. Very much.
That's a nice, another content creator I follow, he called that a little button. And that is a nice button. It's not pure gold, but there's almost certainly a decent amount of gold in there.
Worth it. I'm going to add this little guy back to the group, and just look at how clean it looks. I'm already so happy. It's starting to look like gold, which is pretty fun. Next, I want to throw this on the scale just to see how much junk we got rid of and how much metal is left over. So we are at 514.6 grams. The blob has already slimmed down by 18.7 grams, and we have this beautiful flake left over ready to dissolve.
It's amazing. He's lost less than 20 grams of stuff, but it looks way better than just having lost 20 grams. No, it actually looks like metal now.
It's time for the chemistry.
Warning, this video contains methods and procedures that are extremely dangerous. I'll be handling acids that are incredibly corrosive, toxic fumes are present, as in they can kill you, and that's bad. Please.
He's right. He's working with some pretty nasty stuff.
Please do not try this at home.
Okay, aqua regia, that is royal water. There aren't many things that can dissolve gold, but this combination of acids is one of them.
I start by adding 3 parts hydrochloric acid to my metal. Next comes 1 part nitric acid, and the reaction is swift. This is aqua regia, a liquid so corrosive it can literally dissolve gold, copper, silver, zinc.
So let's take a quick break here and talk about a little bit of chemistry. On this slide, we have the chemical reaction of aqua regia, which is our nitric and hydrochloric acid, with gold metal. This is gold metal, it's solid metal on the left. So the gold metal on the right is an ionic form called tetrachloroaurate. Gold has gone from the metallic 0 oxidation state to the gold in the +3 oxidation state. The video will call this dissolving, but this is not dissolving. Think of dissolving sugar. You add water and the solid sugar goes away. If you evaporate the water, you get the solid sugar back again. In aqua regia, the gold is chemically reacting. It is oxidizing from its 0 oxidation state to +3. The resulting gold ions have an orange color, which will be important later in the video. What else is happening? The nitric acid is forming NO2, which generates a nasty kind of red-orange gas, which we'll see forming over the reaction. Okay, let's get back to the video.
The reaction is giving off some beautiful orange fumes, and these are definitely the ones I don't want to inhale, which is why I'm doing this entire project under a fully vented fume hood. The orange fumes are...
So those fumes are from NO2. Notice that the solution, I said this gold solution would be orange, and yet that's green, clearly green. What's happening here? Well, apparently this metal contains a lot of copper. And copper, when it breaks down an acid and becomes oxidized, it tends to form blue and green solutions. And the color of the copper solution is simply masking the fact that there are definitely orange gold ions in there. We just can't see them because of all the copper. So there's other stuff in there, not just gold.
An indicator that the reaction is still going on. So I let this boil for multiple hours until the orange completely dissipated. This is the exact moment that reality started to sink in. I had been dissolving this metal for hours, and look how much is undissolved. That's when I truly realized that this wasn't going to be an easy project, this wasn't going to be quick, and I was in it for the long haul.
So the long haul, why is this so slow? Why is this a surprise? Well, remember when he made this gold shot and he poured the molten metal into that large cooler, they got smaller the second time he did it, but I wouldn't call those really small shot. So he has less surface area in the metal, and less surface area means that there's less surface to react with the acid. Therefore, it's just slower to react.
Mixing together a fresh batch of aqua regia, I'm going to move my metal over to a hotter burn plate, and I figured the increase in heat would make the reaction go quicker, and boy was I right.
So anytime you heat things, I always think of one of my old lab mates, Mike Postage, who used to call heating things, he called it thermal encouragement. And so here we are, he's providing some thermal encouragement to this reaction, and it makes a difference. Things go faster when they're hot. So, remember Mike Postage. It's gorgeous.
It's very necessary to make sure that the nitric acid is completely boiled out of the solution, and this takes hours, but it's something that is going to be imperative for a later step in this video. Pouring off my second batch of liquid metal, I can see that the reaction did a lot better this time, and a lot more material was dissolved. There's just a little bit left.
Okay, I'm going to stop him right there. If you look kind of towards the top middle of the screen, it looks like there's a coin on its edge. That is almost certainly that little gold button that he melted when he recovered some extra gold. So that's probably the biggest piece in there. And as the biggest piece is going to take the longest to dissolve, and we're still seeing it in the reaction. So it'll go eventually, but it's going to take some time.
I'm going to do this one last time. Using a stir rod and swirling around the beaker and not having much resistance was truly a wonderful feeling. All of the metal has been dissolved, and it's time to move to the next step, which is separating the liquid from the silver chloride.
Okay, let me go back just a little bit right there. So you can see in that funnel, there is filter paper, but it looks to me like there are actually 2 sheets of filter paper in that funnel. And so I suspect as he's working with this funnel, he's wondering, how come I'm not getting rid of all my solids when I put them through this funnel? And so the answer could be, well, let's just use 2 sheets of filter paper. Ironically, the real answer is that you want to do the opposite. You want smaller filter paper that just barely covers the hole, not more filter paper. But it's getting the work done. It's just not as smooth perhaps as he hoped. He doesn't say this, but I'm sort of inferring based on what I'm seeing in the video.
Silver chloride. And I do this by pouring everything over a filter again. As you know, I had to dissolve all this metal in multiple attempts, so I have lots of different beakers filled with dissolved metal, and I will pour them all individually through this filter, capturing as much silver chloride as I can. Now there's actually...
So he's collecting the silver chloride. There are different ways of refining gold, and you don't always have to get silver chloride. Silver chloride comes in the picture because he has silver ions in the presence of chloride ions, and those combine to form silver chloride, which has terrible aqueous solubility. I kind of like seeing the silver chloride here because it's a reminder to the days of general chemistry, where everybody in general chemistry, when they learn about solubility rules, they learn about silver chloride because it's the poster child for aqueous insolubility. So I like that he's going through these steps, but it does introduce more work for him.
Actually a way to save all this silver chloride and refine it and turn it back into pure silver, But that's going to be maybe for another video. We're only really concerned about gold in this video. And now that all the liquid has been filtered, it's time to add some sodium metabisulfite to this liquid.
Okay, sodium metabisulfite. Let's go to another slide and talk about a little bit of chemistry and what sodium metabisulfite is going to do to these gold ions. On this slide, we have the reaction that's going to lead to our precipitation of the gold. So this begins with metabisulfite. That's that substance there. And we're going to react this with our gold ions, which are in solution, as well as water. And we'll get our product out, gold, and this is our solid gold. And that's what precipitates. So this is gold. It's going to be precipitated in its zero oxidation state, and it starts in the +3 oxidation state. And so overall, we are performing a reduction to undo the oxidation we did in the previous step. Now, the reduced gold is metallic gold. Metallic gold is not soluble in water, and so we see a precipitate at the end of this reaction.
This liquid, and this is probably the coolest part of the project. The sodium metabisulfite literally precipitates the gold out of the solution. It's really wild. It's hard to see on this step just due to how dark and green the solution is, but stick around. It's going to look really cool later. This is exactly what we were looking for.
So that solid there, a lot of people call that gold sponge. That is the finely divided particulate gold that comes out of this precipitation process, this reduction of the ion form of gold back into its zero oxidation metallic form.
This is gold, though not a medium of gold I've ever seen or used before.
More filtrations, transfers, rinses, the whole 9 yards. Note that he's getting a lot of glassware. When I'm working in lab and I get a lot of glassware, it normally shows that I'm not 100% certain what I'm doing, because I'm doing transfers and, oh, what's this? And I need something to hold that. And so, you know, I'm not saying he doesn't know what he's doing, but he's feeling his way through this process. And you always need another piece of glassware to hold something else. So it gets messy.
After precipitating the gold out of all my different beakers, I decided to combine all of the gold mud into one place, which was really refreshing, honestly, after dealing with so many different beakers. I used a spray bottle.
So that's a good look at all the gold sponge that he's recovered, all that precipitated metallic gold.
Just to make sure I was getting all the last remnants. I was really happy to get to this point in the project. I had sunk so many hours into it and already felt like I was almost done. But my research told me otherwise. You see, in order to achieve a higher purity, I needed to repeat the entire process. I really wanted to quit, but I'm so glad I didn't. Introducing gold refining part 2, the forbidden orange juice.
Okay, forbidden orange juice. He is foreshadowing the beautiful gold color that you get from these gold solutions.
I'm kicking things off with the ever-familiar aqua regia, but the reaction, it looks different this time. It has beautiful, deep, and rich orange colors, and the gold mud, well, it put up no fight in dissolving quickly.
So he noticed 2 changes: 1, the color, and 2, the rate of the reaction. So the color is different because he's removed almost all the copper. So all that green and blue hue is gone, and now he's just seeing the orange from the gold. The second is the rate of the reaction. It's going much faster. That's because this form of gold, this gold sponge, is so finely divided, high surface area, higher rate of reaction than the lumpy form of gold that he had before.
Pouring it over ice, I give you forbidden orange juice.
No thanks. I'm trying to cut back.
You can see there was some silver chloride left over, which validates my decision to repeat this refining process.
I think that silver chloride is an artifact of the poor filtration that's going on with these funnels. So if he had the right filter paper in there, I think he'd get rid of a lot of that solid. We're going to see in a couple scenes up ahead that there's definitely some cloudiness in the material that he's filtering, and I think that's just silver chloride getting past the filter paper. That's kind of cloudy in the bottom there. It does look like orange juice.
Remember the last time we added sodium metabisulfite and couldn't see our gold precipitating very well? Check this out.
Okay, here we go. And again, it's not going to be a big bar of gold falling out. It's this finely divided gold sponge. You can see that the dynamics
Keep adding
of the
scoops while the
chemical
gold collects at
reaction
the
in
bottom.
there.
But there's one really important thing we haven't discussed yet. How do I know when all the gold has been precipitated? Well, there's a test for that called a stannous test. I mix together hydrochloric acid and pure tin, which creates stannous chloride. This solution is incredible.
Okay, let's go look at our last, what I call the last chemistry slide. So on the slide we have our chemical reaction that occurs in the stannous test. On the left we have stannous chloride, and that means the tin is in the +2 oxidation state. On the right we have stannic oxide, and that means we are in the +4 oxidation state. So this is an oxidation, and if the tin is being oxidized, that means something else is being reduced. And what is it? It's our gold. So this is our gold in the -3 oxidation state, and over on the right it's in the 0, and that should be a +3, not a -3. Goes to 0, so this is being reduced. And in this reaction, when you mix your two solutions, your tin solution and your precious metal containing solution, if you precipitate metal, you will see a dark spot. And that is an indicator that you have metals in your solution. And in the case of our video, that means more of the sodium metabisulfite has to be added. So let's go see this in action.
Sensitive to the presence of gold, and I'll show you how it works. I first take a strip of filter paper and I dip it into my beaker that has the dissolved gold. Then I'll add a drop or two of the...
There is another way to do this. In order to prevent contamination of your solution with your paper, sometimes people will use a dropper, and they'll take a drop of the solution that you're wanting to analyze, and they'll put a drop of that on the paper, and then add the test reagent, the stannous chloride.
The stannous chloride, and watch for a reaction. If it turns black, you know there's still gold in your solution. So in this case, there is, and I need to keep adding sodium metabisulfite.
This does take a while.
You want to be careful to not add too much of this, so I kind of decided to stop here for the night, let it collect at the bottom, and just try again the next morning with my test. The next morning, I discovered everything had settled to the bottom. I thought to myself, all the gold surely has to be out. But let's see what the test says.
That orange color kind of looks like gold.
There's still gold in my solution, so I went ahead and added some more hefty scoops and turned up the heat a bit.
It's a pain to have to add more sodium metabisulfite, but it's a good problem. You know, it means you got more gold in there, so it's not all bad news.
And waited for many hours for things to calm down. Admittedly, things are looking very clear now, and dipping my filter paper into the beaker, it emerged colorless, which had me super optimistic. And the stannous test? It confirmed no more gold remained in the solution. Another happy milestone.
Nice.
I poured off the excess liquid and was left with my pure gold dirt, which I then cleaned by boiling it in distilled water. I gave the gold a few different distilled water baths and one bath in hydrochloric acid. This seemed to do a great job at purifying the gold even further before melting.
He does have all kinds of stuff. All that sodium metabisulfite, you want to get rid of any junk that came along for the ride in that. So, you know, there is stuff to rinse off of this gold metal this has, this sponge.
I left the beaker on a hot plate until all the distilled water dried up. And just look at this gold. The color is absolutely incredible. I've truly never seen anything like it in all my years as a goldsmith. This gold is only worthy of a brand new, freshly glazed crucible.
I've tried to glaze a crucible before. It did not go well, so hats off to him for known how to do that.
Igniting my melting torch, it's time to return this gold to solid metal.
So again, it takes a lot of heat. 1063 Celsius, I believe, is the melting point for gold. So he needs every bit of that heat to get this melted down.
I poured the gold into a bar shape, and while it looked nice, it just didn't feel right. This gold came to me as a blob, and it only felt right to return it to a blob. A pure 24 karat blob.
Oh, can you just dump water into a hot crucible like that and not have everything break? I'm sort of surprised at that. I guess it's okay, but I would not have expected this to be the next scene, dumping cold water into that hot crucible.
The mission is complete. I successfully extracted gold. But
that looks way better than that bar. I mean, the bar was great, but he was right. Aesthetically, that is the form that this gold should be in.
there are two burning questions left to be answered. First, how much does it actually weigh? How close did I get to my initial calculation of 222 grams? The final weight? 213.2 grams.
That was a remarkably good prediction. I would not have thought he'd be plus or minus 10 grams of that calculation. I kind of thought there was a chance he'd be over. But to be within 10 grams, that's impressive.
Only 9 grams shy of my initial estimate. This definitely exceeded my expectations. The second question is just how pure is it? Did I achieve 24 karat? So I sent it to a refinery and I got my answer. It came back as 99% pure. Official gold bullion has a purity stamp of 999.9. And I was really hoping to get a purity rating with at least 3 nines, but I discovered afterward that this refiner doesn't grade that high. So while I'll never know for certain, I do take comfort in knowing that 23 karat gold is 95.8% pure, and I'm well above that. It's safe to say that I truly did extract 24 karat gold. This was by far the most ambitious gold project I've ever done.
Well, I'm going to pause there. It's just a great video. That is the end of this reaction video. Thank you so much for watching as always. If there are other chemistry videos you'd like me to react to, then please let me know in the comments. Take care.